Here we go. This is why you've been learning implicit differentiation to this point and all your derivative rules. Now we're going to start to see the application of it. In this lesson, we're going to talk about what are known as related rates. These are problems that strike fear in the heart of so many calculus students, but for no reason. There's actually a really good way of doing this. I'm going to show you that really good way. We're going to go through many different types of examples. Let's jump into this. So we're given a word problem. And in that word problem, it says a large lawn gnome. Yeah, you know who made this problem up? Me. Is tossed into a calm pond, causing ripples in the shape of concentric circles. So you basically have like a circle, and then other circles that go outside of that circle right from the same center, right? The radius r of the outer ripple. So I like to draw a diagram where I can. So that'd be this radius right here, is increasing at a constant rate of 0.5 meters per second. So it's pretty fast actually. It's like whoop, like that. When the radius is 3 meters, at what rate is the total area of the rippling water changing? Oh, that's a lot. When I'm, encountering related rates problems, what I like to do is I love, and I've got a quote down here, to relate the variables in the problem with the proper equation. Oftentimes in class, that's going to be a geometric equation. So let's find that equation first. Other teachers teach this differently. They look for the variables and they list them out first, not me. I like the equation first. It kind of forms a shopping list, if you will. So we've got a circle, and we're being asked about the area, and we're being given the radius. So the area of a circle is equal to, don't know why I'm writing this so big, pi r squared. Okay, well, why is that important? What we're being asked about is, what rate is the area changing? So you need the derivative of this function, but the question is, with respect to what? In all the related rates problems that we're going to be dealing with, we're going to assume that all variables are changing because of time. So as time goes by, the area is expanding. And as time goes by, the radius is expanding. So every variable will be implicit because we're taking the derivative with respect to time. So we're taking d by dt, which means everything has the chain rule attached to it. So the derivative of a with respect to time is dA dt, which is just like when you had a y with respect to x, was dy dx. This is d, that variable, dt, equals pi is a constant, let it hang out, and then you've got r squared. The derivative of that is 2 times r, but it's with respect to time. So this is like y with respect to x. It would be y and then a y prime, so r and then an r prime, or a dr dt, or as I like to say it, derivative, if you're saying it phonetically. Now that we've got everything out, we took derivative because we're looking for rates. Now we go and look to see what variables we have and how they relate with this. So we know that the radius is increasing at a constant rate of 0.5. Increasing implies that's a rate, a derivative, a velocity, if you will. So dr dt, the rate at which the radius is changing as time changes, is equal to 0.5. And you can put units if you want. When the radius is 3 meters, so at the instant the radius is 3 meters. Now you might ask, why didn't we plug this in to start? You never, ever plug in a constant value like that into a changing variable. So we got r equals 3, but r is changing. If we had plugged this in before we took a derivative, we would have taken a derivative of 9 pi. 3 squared is 9 times pi, which would have been 0. But the radius is changing. It can't be that the area is not changing and that it's 0. Never ever plug in a number into a variable that is changing until after you've taken the derivative. All right? Otherwise, you're saying that the radius is never changing by plugging it in here. You're saying it's always 3, which is not the case. We want to solve for the rate at which the area is changing, or dA dt. So I like to list out what I'm solving for, but not until after I've taken a derivative and take stock of what I have. Now dA dt, it's okay that I don't have that, or da da ta, is equal to 2 pi times the radius at that instant, which is 3, times dr dt, which is 0.5. And we multiply everything together. 2 times 3 is 6, times half of that is 3, with that pi. And what would your units be? Units are very important to a lot of professors and teachers, and rightly so. Well, that would be area, which in this case we're talking about meters. So that'd be square meters. Use this as your units, right? Square meters per time. Time was in seconds per second. So meters squared per second. And that's it. So that means the area of the pond is increasing by 3 pi meters squared per second at the time that the radius is 3. Pretty sweet. And again, always make an equation that relates the variables, often a geometric equation, then look to see if we're safe to differentiate. And we'll have more on that in later videos. All right, so I'm going to go over one other example with this and give you the steps that I often go through. So these steps are not things I ever want you to memorize, but they're there for you if you need them. I'd rather you just go through the ideas as I go through it. But if you need steps, here they are. You draw a picture. We did that last time. You put the variables down for the changing amounts and the numbers down for the constant amounts. Again, that is not what I usually do second. This is what a lot of teachers do. I usually skip right to 3 and write an equation that relates the variables. That's where I did a equals pi r squared in the last part of the video. I like to say look both ways before differentiating. If it's safe to differentiate, meaning the derivative won't have a product rule, won't create a whole bunch of other variables, then go ahead and do so and differentiate. If we're going to have a messy derivative, we might need to solve the equation for one variable in terms of another. We'll get to that down the road. This is just blanketing all problems. Then you're going to plug in the values that we have from the word problem to see what you need to maybe still solve for and to see what you have. And finally, you're going to solve for the desired variable. So, do I memorize these steps? Heck no. I'd rather you just rock the problems as we're going over it, starting with the equation, taking the derivative, and using logic. All right, so we'll see what that's all about in later videos. I'll go over a lot of examples, but those are your general steps. Figured I'd show them to you. Okie doke. Last problem in this video. Y equals x squared minus 5 is a function where x and y are both differentiable functions in terms of t, so basically time. Find dy dt. That is, well, given. So find dy dt given that x equals 3 and dx dt equals 2. How do we do this? Essentially what's happening here is we're moving along the curve x squared minus 5. Like imagine that you've got some point at x equals 3, so that would be here. And what we're doing is we're moving along the curve. We're moving to the right, almost like this particle is being pushed to the right too. So what's happening with the y value? Are we moving up or down, and how fast? That's the visual. You don't have to know that. So we have y equals x squared minus 5. We're going to take a derivative with respect to time, because again, we want dy dt. Everything is implicit in this case. So the derivative of y with respect to time is dy dt, or y prime of t. That's equal to the derivative of x squared will be 2x, don't forget, times dx dt, minus 0, because the derivative of 5 is 0. I'm going to go over at the end of this video why it's dx dt that you have to throw onto there, why that makes a lot of sense, and it's not just x. So now we're going to plug in the values we have. You've got x equals 3, and you've got dx dt equals 2. So that's equal to dy dt. And that, of course, is equal to 12. We don't have no units at all, so it's just 12. So what that means is when we push the particle to the right 2, we end up going upwards at a rate of 12 meters per second, miles per hour, whatever it is. That's it. Now, why is it that we have this implicit with x? I thought it was just 2x. Well, if you take a look at this, x squared, and maybe I'll get rid of the y, let's just hyper-focus in on the x value. So the x of t, that x squared part right here, I'm just zooming in on this, it's assumed that x is a function of t. So when you take a derivative of this, you get 2 times x of t times the derivative of the inside, x prime of t. And another way of writing that is 2x dx dt. So this is why whenever you take a derivative with respect to t, all of the variables we're assuming are in terms of t. In the problem that we did before with the circle, we assumed that r was a function of t, that it was r of t. And so when you take a derivative of that, you've got to multiply by r prime of t, or dr dt. All right, I thought I'd touch that up just for those of you wondering, why do I have to do dr dt? Why do I have to do dx dt? There you have it. See you in the next video.